Hi everyone, this is Mrs. J, and today we're going to start learning about implicit differentiation. Alright, so I have a warm-up for you to try, so go ahead and pause the video and give it a shot. Alright, go ahead and check your work here. So to find a value where the tangent line is horizontal, they're essentially asking you to find when your derivative is equal to 0. So first, here's the process of finding the derivative. We do have to use that quotient rule. And here's our derivative down here. I will bubble it. And then we're going to set that derivative equal to 0, again, to figure out where the slope of our tangent line is 0, or where our tangent line is horizontal. So this is going to be equal to 0 when the numerator is equal to 0. So now we're just solving this trig equation. The sign of what angle is equal to -1/2. That happens 2 times in quadrant 3 and 4 when our reference angle is pi/6 or 30 degrees. And of course, that's going to repeat every rotation forward or back. So we actually have an infinite number of answers. We can describe them using this repeating angle method by adding 2 pi n to either of our angles, where n is any integer, which means that it covers any rotation forward or backwards. So these would be our answers. All right, I have a little extra warm-up for us today. So again, pause the video and give these a try. All right, go ahead and check your answers here. So for part A here, we do need to use the chain rule. So we take the derivative of the outermost function, so that exponential function, and you get this. Notice that I'm keeping secant of theta over 2. And then you take the derivative of the next innermost function, which would be our secant function, and the derivative of secant is secant tangent. Notice I'm keeping theta over 2 here. And then we take the derivative of our innermost function, which is essentially just 1/2 theta, and the derivative of that is 1/2. Then I just rewrote my terms here. And then for part B, we have an equation where we have x in terms of t and y in terms of t. So to find dx dt, we're simply just taking this derivative, the derivative of x in terms of t, so we can use the power rule here. Same for dy dt. This is y in terms of t, so we just do power rule. Now, if I'm asking you to find dy dx, that means that we need an equation that describes y in terms of x. So here I have x in terms of t, so I can actually solve for t squared and plug it into our other equation, and then I can simplify, and now I have y in terms of x. So you do need to find an equation for y in terms of x to find dy dx. And then from here, you're just using power rule, so definitely a little tricky. Just an interesting thing I want to note, that dy dx, you may have noticed, is actually dy dt over dx dt. And dy dt, as we found, was 6t. Dx dt is 2t. And if you divide that, you get 3, which we found is dy dx. We can't really just cancel out this like we would a rational equation, but you can kind of see that if we could do that, it would equal dy dx. So just something to kind of help you make connections over what all of these things mean. So today we're going to start working with new types of equations. So previously we've been working with all explicit equations. So equations that essentially you were able to solve for y. So this is when the dependent variable, which in our case is y, is defined explicitly in terms of our independent variable, which is x. So everything we've been working up to now is always y equals something in terms of x or other variable. So an implicit equation is when our dependent variable is not defined explicitly in terms of our independent variable. So notice that these two equations are actually the same, right? If I multiply both sides by x here, I get xy equals 1. So this is an implicit form of the same equation. So again, we are going to be working now with equations that it doesn't necessarily say y equals, and we're going to learn how to differentiate in those forms. So before we use implicit differentiation, I want to look at an implicit equation. So this is an equation of a circle, x squared plus y squared equals 25. So if I ask you to find this derivative and we don't know implicit differentiation yet, what you would need to do is you would need to solve for y. So we can do that. It's not too hard. So we would first isolate y squared, so 25 minus x squared, and then we would take the plus or minus square root of both sides. So to find this derivative, we would actually need to find the derivative of the positive and negative version. So we'll do positive square root of 25 minus x squared and the negative square root of 25 minus x squared. And we will need to use the chain rule for both of these. So to find this one, it's y prime equals, so we see that this is really, we could rewrite this as 25 minus x squared to the power of 1/2. So we can take the derivative of our radical function using our power rule. So it becomes 1/2 times 25 minus x squared to the power of negative 1/2. And then we need to take the derivative of the inner part of our function, that quadratic, which we can also do using our power rule. So it becomes negative 2x. So here y prime would equal, well here the 2 and the 2 cancel out. So we are left with negative x over the square root of 25 minus x squared. So you can see that I just brought this down to the denominator and then rewrote it as a radical again. We could do that same process for our negative form. Same thing, except it's going to be negative 1/2 times 25 minus x squared to the power of negative 1/2 times negative 2. So this time the negatives cancel out, and I'm just left with x over, I'll do square root of 25 minus x squared. So we could think of this derivative, so we could say dy dx is the plus or minus x over square root of 25 minus x squared. So it is possible to find the derivative of this implicit equation by first solving for y. So we rewrote it in explicit form and then we found the derivative. However, it is also possible for us to find this derivative in a different way, which is what we'll be learning today. So we are going to be using implicit differentiation when it's really difficult for us to solve for y. So when we have an implicit equation and it just makes it really, really hard to rewrite it in explicit form. So when we're doing this, we're going to just simply differentiate both sides of our equation with respect to x. So every single term we're going to differentiate again with respect to x. Sometimes we will need to use our product rule or our quotient rule, our power rule, our chain rule, but we're going to differentiate every term with respect to x. However, the new thing here is when we are differentiating a term with y. So this is the part that we need to watch out for, because when we're differentiating a term with y, we actually need to use the chain rule because y is a function of x. So it's almost like it's like a composition of functions. So for example, if you have a term in your implicit equation that is y squared, so you're doing the derivative of that term. So we need to do the chain rule. So to find the derivative of y squared, first we look at the outer equation, which we can differentiate using our power rule, so that becomes 2y. But again, because y is a function of x, we then need to take the derivative of y, so dy dx. Which we could also write as 2y, y prime. So to sum it up, the important thing with implicit differentiation is to always apply that chain rule when we're working with a term with y. So you will always end up with that y prime as part of our derivative of our y term. So now we're going to try to find the derivative of that same equation of our circle using now implicit differentiation. So we're going to go through, we're going to take the derivative, we're going to differentiate every term on both sides. So we're going to find the derivative d dx of x squared, and we're going to find the derivative of this y squared term, and we'll find the derivative of 25. So we're going to differentiate every term in terms of x. So differentiating this is just like differentiating an x term with an explicit equation. Here we can just say that this is 2x. We can just use our power rule. But again, here is where we need to watch out because technically we do need to use our chain rule here. So to find this derivative in terms of x, first we need to differentiate y squared using the power rule. So 2y, and then we need to differentiate the inner equation, which becomes dy dx. So we have 2y dy dx, or we could write that as 2y y prime. And then here we can differentiate 25 just like we would any other constant term. It's just 0. So from here, all we're going to do to find that derivative is now we just need to isolate this term because this is our derivative. So we can do that by first, we can subtract 2x from both sides. So we have 2y times dy dx equals negative 2x, and then we're going to divide both sides by 2y, and we end up with negative x over y. So I know this may seem like we have a completely different answer than we did the first time, but oftentimes when we are differentiating using implicit differentiation, our derivative will be in terms of x and y, and that's okay. So if you look back at example 1, we found that our derivative was plus or minus x over the square root of 25 minus x squared. But if you remember here, that y is equal to the plus or minus square root of 25 minus x squared, that these actually are the same. So this derivative is simply in terms of x and y, and this derivative is completely in terms of x. So remember, it is completely normal for your derivative when using implicit differentiation to be in terms of x and y. All right, let's try another one together. So if you look at this implicit equation, this would be extremely difficult to solve for y, so we definitely want to know how to use implicit differentiation. So we're going to go in and we're going to, again, take the derivative of each term in terms of x, so the derivative in reference to x. So d dx of x cubed plus d dx of y cubed equals d dx of 6xy. So finding the derivative of the term x cubed, pretty straightforward. We just use our power rule. Here we do need to apply our chain rule because really this is a composition of functions because y is a function of x. So first we're going to differentiate using our power rule, so 3y squared, and then we're going to differentiate our inner function y, which is just the derivative of y. This time I'll write it as y prime. And then here we are going to need to use our product rule. So we need to use our product rule because we have the product of two functions, 6x and y. So we can take our first function times the derivative of the second, which is y prime, plus our second function, which is y, times the derivative of the first, which is just 6. So now we've differentiated each term in terms of x. So now we just need to solve for y prime. We need to isolate y prime. So to do this, we're going to want to make sure we move all of the terms with y prime to the same side of our equation. So we can do 3y squared y prime minus 6x y prime. And we'll move all of the other terms to the other side. So we have 6y minus 3x squared. And then from here, we can factor out y prime. It's a GCF. And then we can isolate y prime by simply dividing by this remaining factor. So 6y minus 3x squared over 3y squared minus 6x. So now from here, all we need to do is simplify. So notice that all of our terms are divisible by 3. So we can say y prime equals 2y minus x squared over y squared minus 2x. All right, let's try another one together. So here's another case where we definitely would want to know how to use implicit differentiation to differentiate. So let's take, again, the derivative of every single term in terms of x. Okay, so here d dx of sine of x would just be cosine of x, so we don't need to worry about the chain rule for this one. For our next term, we do need to worry about the chain rule, so we're going to differentiate our outer term first, which is cosine. So actually, let me change this to a negative because the derivative of cosine is negative sine of y, and then we need to take the derivative of our inner term, so y prime. And then on the right side, we are going to need to use our product rule again. So first term times the derivative of our second. And again, we need to use our chain rule here. So the derivative of cosine is negative sine. And then we also need to do the derivative of our inner function, so y prime, plus the second function times the derivative of the first. Derivative of sine of x is cosine of x. So from here, the rest is pretty easy. We just need to isolate y prime because we are trying to find y prime. So we're going to move all the terms with y prime to the same side. So this is a negative term, so we can actually add it to the other side. So we get the sine of x times the sine of y times y prime. And then we have this y prime term here, so we'll keep that. So the sine of y times y prime. And then we're going to move this to the other side. So we have the cosine of y times the cosine of x minus the cosine of x. So now I can factor out y prime. So y prime times the sine of x times the sine of y minus the sine of y equals, and then here, just to save us a step later, I do see that there is a common factor of cosine of x, so cosine of y minus 1, and then all I need to do is divide this remaining factor to the other side, and in that same step, I'm also going to factor out a common factor of the sine of y, just to simplify my derivative. So we have sine of y times the sine of x minus 1. So here is y prime. All right, let's try another one together. Here's our equation, and again, we're going to find y prime. So we're going to differentiate both sides with respect to x. So here we do need to use the chain rule. So we're going to start with our outer function. The derivative of sine is cosine. And then we need to differentiate our inner function. So the derivative of x is 1 and the derivative of y is y prime. Then on the right side of our equation, we do need to use our product rule. So we do first equation times the derivative of the second plus the second equation times the derivative of the first, and to find the derivative of the first, we need to also use the chain rule. So it becomes 2y times y prime. So now we do need to do a little extra work to help us isolate y prime. So we can start, let me highlight our y primes. We are going to start by distributing this, the cosine of x plus y, to this. So this gives us y prime cosine of x plus y plus cosine of x plus y. I distributed and I rewrote the terms in the other order. Equals, I'll move our negative out front, negative y squared sine of x plus 2y cosine of x y prime. So now I want to move this term to the left side of our equation. So minus 2y times the cosine of x times y prime equals, and then I'm going to move this to the right side of our equation, negative y squared sine of x minus the cosine of x plus y. Now we can factor out y prime. So cosine of x plus y minus 2y cosine of x. And we are almost there. Let's divide away that remaining factor. So y prime equals negative y squared sine of x minus the cosine of x plus y, all over the cosine of x plus y minus 2y times the cosine of x. So I know that these answers look really kind of ugly and scary, but if you look at the individual steps, nothing is too difficult. It is really important that you go one step at a time, and it's also extremely important that you keep your work clear and organized. All right, let's try one more together. So here we're going to find the equation of the line that is tangent to this equation, x squared plus xy minus y squared equals 1 at the point 2, 3. So first we are going to need to find the slope of our line, and to do that we need to find our derivative. So first let's find y prime. So we're going to differentiate every single term on both sides of our equation. So to differentiate x squared is simply 2x. To differentiate this term, we are going to need to use our product rule. I'll make a little note of that here. For this one, we use our product rule. So it's going to be first times the derivative of the second plus second times the derivative of the first, which is just 1. The derivative of x is 1. And then here we also need to use our chain rule for y squared, just like we have been doing. So it's minus 2y times y prime, and the derivative of 1 is just 0. So now we're going to want to isolate the y prime terms on the left side of our equation. And we'll move everything else to the other side. We can factor out y prime, so y prime times x minus 2y. And we'll divide away our remaining factor. So y prime equals negative 2x minus y over x minus 2y. So this is the derivative, and this will allow us to find the slope of our line at any point. So now we're going to want to substitute 2, 3. I'll make a note of that here. We're going to substitute x with 2 and y with 3. So we get negative 2 times 2 minus 3 over 2 minus 2 times 3. And here we get a slope of negative 7 over negative 4, so 7 over 4. So again, for this value, this is the slope of our tangent line. At the point 2, 3. So now we just need to make the equation. So we can do y minus y1 equals m times x minus x1. And we can leave our equation like this, or you could distribute and rewrite it in slope-intercept form. All right, I have one more for you to try on your own, so please pause the video and hit play when you're ready to check. All right, so go ahead and check your work. This would definitely be more of an AP style question because it involves, a deeper comprehension of a number of different topics. So first, because they're asking about whether or not the slope is defined, we do need to find that derivative. So we can find the derivative of this equation using implicit differentiation. So you can see we did here. So the derivative of our function is 2x over 2 minus the cosine of y. So if we want to show that it's defined at every point, well, let's talk about when this could become undefined. So a rational function is undefined if the denominator is equal to 0. So if you set this denominator equal to 0 and you solve, you'll see that you get something that is not possible. The cosine of y will never equal 2 because the range of cosine is between -1 and +1. So it's never going to be possible for our denominator it equals 0, which means that this function is always defined, which means that our slope is always defined. All right, that is all for today's video. Thank you so much for watching.